In this video, we'll use the hoteling model to look at product positioning. So far we assumed that the firms were located at 0 and 1. What if we allow firms to choose their location? How will they position their product? Will they choose to locate together or far apart? So to answer these questions, we're going to consider a two-stage game. In the first stage, firms simultaneously choose their locations, LA and LB, and in the second stage, firms simultaneously choose PA and PB, their prices. So far we've looked at stage 2 under the assumption that LA is 0 and LB is 1. It turns out we can split up the effect of a change in location on profits into two parts. So the first effect we call the direct effect. So fixing prices, a change in a firm's location is going to affect its demand and therefore affect its profit. There is also a strategic effect. A change in the firm's location is going to affect the second stage price competition. In particular, the other firm is going to change their price, and this is going to affect the firm's demand and therefore its profits. So we'll start with the direct effect. So here we're fixing prices and looking at the effect of a change in location. So let's fix the prices at the Nash equilibrium prices when the firms are located at either end of the line. What is the effect of a small change in location of firm A from LA equals 0 to some other location, LA dash, which is larger than 0? So here we have our diagram. We're fixing the prices at the Nash equilibrium levels. This is A's initial location at 0 and B's location is at 1. This is the indifferent consumer and A's demand is 1/2. Now let's consider a small change in location for firm A. So they're going to move to the right to LA dash. So what effect does this have on firm A's demand if we fix the prices at these Nash equilibrium levels? Well, as A moves to the right, it's going to capture more consumers between it and firm B because the firms have the same prices. The indifferent consumer is going to be halfway between the two firms. So this was the halfway point at a half when they were at 0 and 1. Now that firm A has moved to the right, the halfway point is also going to move to the right. In fact, it's going to move to the right by half the distance that A has moved. So X dash is the new indifferent consumer. Now we can draw the delivered cost line. So what would it look like now that firm A is not at 0? Well, for a consumer located exactly where A is located now, the delivered price is just PAN. And then as we move away to the right or the left, the delivered cost is going to go up by T per unit of distance. So it's going to look just like it did before as we move to the right, but as we move to the left, it's going to be reflected. So this red thing is the delivered cost line of firm A. It's the price of firm A plus T times the absolute value or the distance between X and LA dash. So we can see the intersection of the delivered cost line for A, this red line, and the delivered cost line for B is at this point, which gives us X dash. So the change in profits of firm A from this change in location are just the area between Xn and X dash, the increase in demand, multiplied by the price minus the cost, which remember is 0. So it's this rectangle here. This is the direct effect. So the direct effect is positive. If prices are fixed, any movement of A towards B is going to increase A's demand and hence its profits. Now, if we consider a situation where consumers are distributed uniformly, as we've assumed so far, and prices are fixed and equal, then the only Nash equilibrium is for both firms to locate at the center, at a half. So here we're going to look at something called the principle of minimum differentiation. So in the notes, that result that firms are going to want to locate in the middle is the principle of minimum differentiation. If the prices are fixed, they want to be in the same place. Here we have a beach with sunbathers lined up evenly along the beach, and there are two ice cream sellers. So let's suppose initially that the ice cream sellers are located at 25 meters and 75 meters. The beach is 100 meters long. These are the locations that minimize the distance any one sunbather has to walk in order to get an ice cream. Are these locations a Nash equilibrium? Well, no. If we consider the ice cream truck on the left, if they move to the right, then they're going to capture more of the sunbathers between their two ice cream trucks, because now they're going to be closer to more of those sunbathers between the two trucks, and therefore they're going to increase their demand and their profit. So this is that direct effect. They've captured an extra sunbather here. But the same is true for the other truck. If they move to the left, then they're going to capture more sunbathers. So there can't be an equilibrium where there is anything between the two trucks, because there's always going to be incentive for them to move closer to each other. And so we have the only Nash equilibrium is where they're in the middle of the beach. There's no incentive to deviate here because they're getting half the demand, and any move to the left or the right would lose demand to the other ice cream truck because there would be some sunbathers between them. Is this efficient? Well, no. The initial locations were efficient. They minimized the distance anyone had to travel, which also minimizes the average distance people have to travel. Here, the sunbathers at the ends of the beach have to travel 50 meters, whereas before the most anyone had to travel was 25 meters. This is the principle of minimum differentiation. If prices are fixed, then firms want to locate in the middle in the same place. And this is inefficient. So this idea can be applied to things other than firms selling a good. We can think of political parties. So suppose these were two political parties and voters had a preference for the left or the right, and the line was such that 0 represented the left politically and 1 was the right politically, then this result would imply that political parties would locate in the middle. And this is simply because it enables them to capture more of the market share, more of the voters, which is the direct effect. So now we're going to look at the strategic effect. So because prices aren't fixed here, prices are chosen after locations are chosen. The price chosen by B in the second stage is going to depend on the location chosen by A in the first stage, as well as its own location. So if A changes their location, B's price is going to change. It will no longer be optimal to price at PBN, and this is going to affect A's demand curve and profit. The change in A's profit is the strategic effect. So the strategic effect in this model is negative. Any move towards the other firm is going to increase price competition. So firm B will lower their price. This will reduce A's demand because the two goods are substitutes, and this will lower A's profit. So as an extreme case, to see how this works, consider what happens when A moves all the way from 0 to 1. Then both firms are going to be located in the same place. We will have the standard Bertrand result, and firms will price at marginal cost, whereas when they were located at 0 and 1, they were pricing above marginal cost. So price competition increases, and profits will be decreased because of that. So let's consider a small change in location. So we've got this move of A from LA to LA dash. We have the direct effect here in blue, and this blue line is the demand curve of firm A after its change in location. So now let's consider the strategic effect. So the strategic effect is that firm B's price is going to fall, and this is going to affect A's demand curve. It's going to shift in. So the red line is the new demand curve, and so at these prices the demand is going to fall to XN dash, and this is going to result in a reduction in the profit equal to this red area here. But the reduction here in profit from the strategic effect is less than the increase in profit from the direct effect in this case, and so it would be profitable here for firm A to move to the right. So this red area is the strategic effect. I should emphasize here that we're looking at a small change in location, but I've drawn it as quite a large change just so we can see the areas in the diagram. So we have these two effects of changing position. The direct effect gives an incentive to locate close to each other. Moving closer to the other firm will capture more of the consumers in between. Whereas the direct effect gives an incentive to move apart because moving closer together increases price competition, moving further apart decreases price competition. So there's this incentive to differentiate because of the strategic effect. The balance of the two effects is going to determine whether firms want to locate close together or far apart. What we do know is they don't want to locate in the same place because that's just the Bertrand model and they get zero profits. But exactly where they want to locate is going to depend on the balance. The relative size of those two effects depends on the transport costs and the distribution of consumers. So here we've assumed there's a uniform distribution. But you could probably see if more of the consumers are located in the middle, then they're probably going to want to locate closer to the middle of the distribution. If they're more spread, then maybe they want to locate further apart. Now, you might wonder, what is the equilibrium of the two-stage game here? Well, it turns out that it's actually complicated. There's an issue when the firms are located quite close together. There's no pure strategy, Nash equilibrium and prices. There's a mixed strategy. But if we alter the model slightly so that the transport costs are quadratic, so now the transport costs look like this for firm A, then the firms actually want to locate at 0 and 1. There's the principle of maximum differentiation.